This is Lecture 3J for Calculus 1 on the derivative of inverse trig functions. To find these derivatives, we use implicit differentiation. And then once you've used the implicit differentiation, you need to rewrite them. And the trick is to rewrite the answer that you got from the implicit differentiation using common trig identities. You should know by heart sine squared plus cosine squared equals 1, and all the others can be derived, such as secant squared equals 1 plus tangent squared. But just remember, sine squared plus cosine squared equals 1, and you'll get a lot of mileage from that. So the problem is that y equals the arcsine of x, and we want to find dy by dx. So we rewrite this as sine of x equals y, which is just the statement that y equals the arcsine of x. Now we use implicit differentiation. Remember, in implicit differentiation, we apply the differential operator to both sides. So here we have d by dx being applied to the sine of x. Right. So in this case, we have the composition of an outside function sine x and an inside function y. We take the derivative of the outside function and get cosine y. Then we have to take the derivative of the inside function and we get dy by dx because y is not specified. So again, this is using that implicit differentiation. Sine is the outside function, y is the inside function. The derivative of sine is cosine, evaluated at y, and then you have to multiply by the derivative of y. On the other side of the equation, d by dx of x is 1. So you're done. Now solve for d by dx. So I've got dy by dx, the derivative I wanted, equals 1 over the cosine of y. Well, sometimes we end up with y in the answer for the derivative, but in this case it's not necessary. Use the identity cosine squared plus sine squared equals 1 to write cosine y as the square root of 1 minus sine squared. Now from above, from here, you know that sine squared y equals x, so you can solve, so there you can put the x in, and that's the answer. dy by dx equals 1 over the square root of 1 minus x squared. So the whole procedure, and this holds for all those inverse trig functions, is to write it in the other way. Y equals arcsine x, write it as sine y equals x. After you do that, make use of implicit differentiation. Then isolate the dy by dx. You'll end up with some function of y on the the right-hand side. But you can use those trig identities to rewrite that function of y in terms of x. Here's another example. Say y is the inverse secant of x. So rewrite this as secant y equals x. Use the implicit differentiation. On this side of the equation, you have d by dx of x, and the answer is 1, so that's done. Over here, you have the composition of secant with y. The derivative of secant is secant times tangent, so I take that right here. Then I have to take the derivative of y with respect to x, and that provides this next term. Now solve for dy by dx, and I get dy by dx equals 1 over secant y times tangent y. Well, from the first part of the problem here, I know that x equals secant y, so I can replace secant y with x, and I did that. Now I still have a tangent in here. I can get rid of that tangent by using this identity. Secant squared equals 1 plus tangent squared. So secant squared is x squared. All right. So what we can say here is tangent y equals secant squared minus 1. Secant squared is x squared, and so we put the x squared here under the square root sign, replacing secant squared of y. Same procedure. Rewrite these arcsines in sort of the forward direction. After that, use implicit differentiation to differentiate both sides. Solve for dy by dx. You'll end up with trig functions of y in the answer. Try to eliminate them by using the definition from the start of the problem and from using trig identities. So here's a summary. It does, of course, look initially very strange that you would be taking the derivative of a trig function and not even seeing a trig function in the answer, but that's how that happens. And these are listed in the book, and you can see them there. They're pretty easy to take the derivatives. I think there's one proof in the homework. Just follow the two examples here and you'll be fine.